Now we are going to take a look at the molecular orbital theory, or the MO theory, as it applies to the conjugated system, the system with pi electrons. So we will first look at the molecule ethene, the compound with a carbon-carbon double bond. So in chapter 1, we've talked about the structure of ethene. The carbons in the molecule will be sp2 hybridized. An sp2 hybridized carbon will be planar. The bond angle is 120 degrees. So all the atoms, the 2 carbons and the 4 hydrogens, are in the same plane. And when sp2 hybridized orbitals are formed, they used one s orbital and 2 p orbitals. There will be still one p orbital left for the carbon, and that p orbital will be perpendicular to the plane. Each of the p orbital on the carbon will have 1 electron, and these 2 p orbitals on 2 carbons can overlap side by side to give the pi bond. So now we are going to take a look at the molecular orbital of this pi bond. So when the 2p orbitals combine to form the molecular orbital in ethene, we are going to have 2 molecular orbitals as well. The first molecular orbital is shown here, where the 2 lobes of the p orbitals have the same symmetry, which I use the positive signs to show here. So in both p orbital portion, they have the positive signs on the same side. That means they have the same symmetry and they can overlap. The second the second molecular orbital will have the opposite symmetry. That means the positive signs are on the opposite side, while the negative signs are also on the opposite side. So the symmetry of the p lobes are different, and this molecular orbital cannot have the lobes overlapped with each other. And because of that, this second molecular orbital will have higher energy than the first molecular orbital. So what's shown here is the overlapping of this p component to give the first molecular orbital, and we call it the pi1 orbital. For the second orbital, the second molecular orbital of higher energy, the symmetry of the lobes prevents the overlapping. In the middle, we call there is a node. The node prevents those lobes to overlap with each other, and this orbital, we call it the pi2 star orbital. The pi1 orbital has lower energy. That's where the electron will go. Remember, when the electrons are filled in the orbitals, they tend to fill in the lower energy orbital first. That's the pi1 orbital. And we do have 2 electrons, so both of these 2 electrons will get into the pi1 orbital, and they are going to pair up. They spin in opposite direction. So the pi1 is the bonding orbital, the orbital that's used to form the bond, the pi bond in this case, of course. While the pi2 star orbital has higher energy, and we don't have any electron left because originally each p orbital has one electron. We have 2 electrons total, and we've used these 2 electrons already, so there will be no electron used to fill in the pi 2 star orbital. The pi 2 star orbital will be empty, and this is what's called the anti-bonding orbital, the orbital of higher energy that cannot be used to form the bond. Another concept in the molecular orbital theory is the HOMO and the LUMO. Basically, we call pi 1 as HOMO orbital. HOMO stands for highest energy occupied molecular orbital, while LUMO stands for lowest energy unoccupied molecular orbital. Okay, those are HOMO and LUMO are the abbreviations for these terms. So HOMO means it's the orbital with electrons, but it has the highest energy. So compared to other orbitals that occupy sigma electrons, this is the highest energy orbital with electrons, highest occupied molecular orbital. While the LUMO is unoccupied, lowest energy. So it's the lowest energy unoccupied molecular orbital. This picture is taken from your textbook, figure 8.10, that shows the molecular orbital of ethene. And as you can see, the bottom is the pi bonding orbital, where the lobes can overlap, while on the top, that's the pi 2 star anti-bonding molecular orbital, there is a node between those lobes, so they cannot overlap. One thing you need to pay attention is that the bonding orbital, the pi 1, has lower energy than a p atomic orbital, while the anti-bonding orbital has higher energy than the regular p atomic orbitals. All right. Now next, we will take a look at 1,3-butadiene. 1,3-butadiene has 4 carbons with 2 double bonds. All the carbons are sp2 hybridized. So all the carbons and the hydrogens are in the same plane. And similar to the previous case, each of the carbon will have a p orbital left that is perpendicular to the plane. And each of the p orbital will have 1 electron. So the 1,3-butadiene will have 4 p orbitals that are perpendicular to each other, and they can overlap with each other, even though we draw 2 double bonds between carbon 1 and 2 and 3 and 4. But in reality, the carbon-carbon bond between carbon 2 and carbon 3 also has some double bond characteristic because the whole system is conjugated, right? That's why we call this molecule as a conjugated diene. Now, the molecular orbital of 1,3-butadiene, because it's made of 4 p atomic orbitals, so we are going to generate 4 molecular orbitals, and each one of them will have some component from each of the p atomic orbitals. The lowest energy molecular orbital is shown here, and the positive signs regarding the symmetry of the orbital are all on the same side. There is no node. The second molecular orbital formed, the symmetry, only two positive signs on one side and two positive signs on the other side. So there will be one node in the middle. The third molecular orbital, we have one positive sign on top, two positive signs at the bottom, and another positive sign on top. And this orbital will have two nodes. The last one, the highest molecular orbital, the positive signs are alternating top and bottom, so none of them can overlap with each other. There are three nodes. So I'm going to show you how the orbitals, how these components can overlap with each other to form the molecular orbital. So the positive sign and the negative sign are all on the same side for the lowest energy orbital. There is no node. The second lowest energy orbital will have one node in the middle. The third molecular orbital will have two nodes, while the highest energy orbital, there will be no overlapping, so there are three nodes. So these are the four molecular orbitals formed from the original four p atomic orbitals. We call these four orbitals from low energy to high energy as pi 1 orbital, pi 2 orbital, pi 3 star orbital, and pi 4 star orbital. You probably have noticed that for the bonding orbital, we just use the regular pi 1 or pi 2. For anti-bonding orbitals, we put a star there to indicate it is an anti-bonding orbital. And originally we have 4 electrons. So we have 4 orbitals, each contain 1 electron, 4 electrons total. And these 4 electrons are going to fill in these 4 molecular orbitals. So they are going to occupy pi 1 and pi 2. Then we don't have any more electrons left. And the pi 3 and the pi 4 as anti-bonding orbital will be left empty. Pi 2 molecular orbital will be our HOMO, the highest energy occupied molecular orbital. Okay, because pi 2 has higher energy than pi 1, and it's occupied. While the LUMO, lowest unoccupied molecular orbital, will be pi 3 star. Okay, pi 3 star has lower energy than pi 4 star, and it's unoccupied. And this is a picture from your textbook, figure 8.11. It shows the 4 molecular orbitals for 1,3-butadiene. From bottom to top, energy lower to higher. And as you can see here, pi 1, pi 2 are bonding orbitals with electrons. And they both have lower energy than the original p atomic orbitals. Pi 3 star, pi 4 star are antibonding orbitals. They are empty, and both of them have higher energy than the original p atomic orbitals.